Before I continue with a discussion of how to handle the complex roots case or complex poles case, let me point out something which you can take as some kind of a correction to a statement that I made earlier, because I would like to keep the practice followed in most control theory books. You remember that we are looking at the quadratic factor a squared plus as plus b for the case when the discriminant was negative, the discriminant delta being a squared minus 4b, that was negative, and because of that we had a pair of conjugate complex poles or roots. Now in this case, when trying to find out the Laplace inverse of the part of the response, one method was to factorize this quadratic a squared plus as plus b into its linear factors and then use the regular partial fraction expansion method for linear factors. But as I mentioned earlier, this introduces complex numbers into the calculation, and although the calculations are not really more difficult, but if you make some mistake somewhere of getting a wrong sign for the real or the imaginary part, and when computing the coefficients of the partial fraction expansion, the final answer may turn out to be complex or even imaginary rather than purely real. We expect that, of course, the speed or the part of the speed that we are looking at will be a real valued function of time. Now such a mistake can be avoided, or rather the use of complex numbers can be avoided in this case, and I indicated to you how that can be done by using the method of completing the squares. So you write s squared plus as plus b as s plus a divided by 2 whole square, and this is called completing the square. In other words, you take the two terms a squared plus as and think of adding one more term so that you get a complete square, and so I have to add a square by 4, and therefore I have to subtract a square by 4, and therefore I will get an expression which is s plus a by 2 squared plus b minus a squared by 4. And here, because the discriminant is what it was, we saw b minus a squared by 4 will be greater than 0. So this term will be greater than 0 or positive, and therefore I said that you could write this as omega n square, where omega n is some real number, and you can choose omega n also as positive. With this, then the s plus a by 2 square term can be rewritten as s plus delta omega n squared plus omega n square, where delta omega n then turns out to be equal to a by 2. So with omega n square given by b minus a square by 4, from this formula delta omega n equal to a by 2, we can obtain the value of delta. Now I told you that this omega n is called the natural frequency and this delta is called the damping coefficient or the damping ratio. Now what I should have really said is that it would be more appropriate to call this omega n the natural frequency and this delta as associated with damping, for a reason that you will see very soon. But this is not normally done. Normally what is done is you argue like this: I have s squared plus as plus b. What if I did not have the term a? So if I did not have the term a, then I will simply have s squared plus b, and then you think of b as square of a positive quantity, which is then called omega n. So I write b as omega n square, and then we will write the term a as 2 delta omega n, and if I do that, then s squared plus as plus b becomes s squared plus 2 delta omega ns plus omega n square, and by taking these two terms, first two terms, and completing the squares, I will get s plus delta omega n once again squared plus, and this time I have added the term delta square omega n square, so I will have to subtract it from here. So I will write it as 1 minus delta square into omega n square, and so finally it will be written as s plus delta omega n squared plus 1 minus delta square omega n square and this is replaced by, let us say, omega 0 square. So, I will have s plus delta omega n square plus omega 0 square. So, if I do it this way, then I have introduced now omega 0 and delta. Sorry, I should have written it as omega n, omega 0 here rather than omega n. So, I will change that to omega 0. And in textbooks, usually this omega 0 is called the natural frequency associated with the quadratic factor, and delta is called the damping ratio. Now, let us see what is the difference between the two. If I write as I did earlier, s squared plus as plus b as s plus delta omega n square plus omega n square, defining omega n square as b minus a square by 4, then the roots are given by minus delta omega n plus or minus j omega n. And so, if I show them in the complex plane, then here is what they look like. The imaginary part, which is the length of this segment, is given by omega n, and the real part or the length of this segment is given by delta omega n. So, in other words, delta omega n is the negative of the real part. Remember, the real part is negative, and omega n is the imaginary part, or the part that, or the number that multiplies j. Now, I have a complex number like this. Depending on the value of delta, what will vary on this diagram? So, as you can see, if delta omega n is larger than omega n, the real part is greater than the imaginary part. If delta omega n is less than omega n, the real part is smaller than the imaginary part. If delta omega n and omega n are equal, then the two parts, real and imaginary parts, are equal. As a result, now if I draw this radius vector to pointing to the pole, and of course there is one and there is the other, so I can draw both of them. If I look at, let us say, only one of them and call this angle theta, then I will have here tangent of theta is given by omega n divided by delta omega n, or 1 by delta. And now I can consider the case where theta is close to 0, that is, the imaginary part is virtually 0, the real part is of course not 0, or theta is very close to 90 degrees, in which case the imaginary part is large, the real part is much smaller. A third case will be theta equal to 45 degrees, when the real and the imaginary parts are equal. So, accordingly, then if delta, which is 1 by tan theta, is much larger than 1, then the system will be such that the real part is greater than the imaginary part. If delta equal to 1, then the system will be such that the two parts are equal, and if delta is less than 0, the two parts will be such that the real part is much less than the imaginary part, and we will see what difference it makes to the response. Now, the same expression can be rewritten as I showed you earlier, but it is rewritten using different symbols or different quantities. Instead of dealing with square root of b minus a square by 4, which I call the natural frequency, one deals with square root of b and calls it the natural frequency omega n. Then the whole expression written in terms of the natural frequency looks very different. It looks like s plus delta omega n squared plus omega 0 square, where omega 0 is not omega n, but it is given by omega n times square root of 1 minus delta square. Now, if I write it this way, then the corresponding poles will be as shown once again, where the imaginary part will be j omega 0 and the real part will be delta omega n. As a result, if I draw the diagram showing the angle theta once again, the angle theta will be given by tangent of theta equal to omega 0 divided by delta omega n. But omega 0 is square root of 1 minus delta square multiplying omega n divided by delta omega n, and therefore this becomes square root of 1 minus delta square divided by delta, which is different from the expression that I wrote earlier. Now, most textbooks follow this convention rather than the one that I mentioned earlier. So, in other words, let me repeat it once again and emphasize. You take the quadratic a squared plus as plus b. I am assuming that b is positive, then the square root of b is called the natural frequency omega n, and then you define a to be equal to 2 delta omega n. This defines delta, and then you write this quadratic as s plus delta omega n square, that is okay, but the second term is not written as omega n square, but it is written as 1 minus delta square into omega n square, or in other words s plus delta omega n square plus omega 0 square. Now in this case, when delta is defined this way, the limits of delta will not be between 0 and infinity as they were in the earlier case, but will be between 0 and 1. Going back to the figure once again, from this figure you will see that the real part is delta omega n, the imaginary part which is omega 0 is square root of 1 minus delta square into omega n, and therefore when delta is very close to 1, the real part will be much greater than the imaginary part, and when delta is close to 0, the real part will be much less than the imaginary part. So in one case delta will approach 1, in the other case the delta will approach 0, and we will see now why one calls that delta, whichever way it is defined, as the damping coefficient or the damping ratio. So let me use the more familiar or the more commonly used abbreviation or symbolism as I have indicated here, s plus delta omega n square plus omega 0 square. So with this then I will rewrite the quadratic, the whole expression for the part of the response that we are looking at as follows. So let us look at the expression for the change in the speed, the Laplace transform of that we were looking at earlier, which is alpha divided by s multiplied by some expression in the numerator divided by this quadratic, and this quadratic now I am writing as s plus delta omega n square plus omega 0 square. Then when we do the partial fraction, we will have a term which will be given by a1 divided by s as before, that is there will be a partial fraction that goes with the factor s, and there will be a partial fraction which I will not write in terms of linear factors, and that will be as follows: s plus delta omega n square plus omega 0 square into a linear term in the numerator. This linear term in the numerator will write as a2 into s plus delta omega n plus a3 into omega 0 square. Now why am I writing it this way? Because as I told you earlier, I am going to make use of a theorem from the Laplace transformation which tells you that if you have a function of time and if you consider its Laplace transform, what happens if the function of time is multiplied by an exponential factor? The theorem says that in that case all you have to do is, in the Laplace transform, you replace s by s plus an appropriate number. So anticipating that, I am writing this expression in this form. Let me mention that result once again. If I have a function f of t whose Laplace transform we are denoting by capital F of s, then if the function f of t is multiplied by an exponential factor, so I write f of t into e raised to minus at, notice the minus a here, and I call this function g, and then I ask the question, what is g of s? What is the Laplace transform of the function g of t at a complex number s? What is its value at a complex number s? Then the answer is g of s is simply f, not evaluated at s but evaluated at s plus a. So what is the point of this theorem now to use it here? If I have a g of s which looks like f of s plus a, that is if I can rewrite a function g of s as f of s plus a, then the Laplace inverse g of t can be recognized as e raised to minus at into the Laplace inverse of f of s. So that is what I am going to use now. So what I have now is the problem of inverting, let us say a2 into s plus delta omega n divided by s plus delta omega n square plus omega 0 square. I want to find out the Laplace inverse of this. So let me write this specifically. Laplace inverse of this function of s, what is it as a function of time? That is what I am trying to find out. Now I see s plus delta omega n. So in place of s plus delta omega n, suppose I had s, then what would I have? I would have a2s divided by, in place of s plus delta omega n, if I had s, I would have s squared plus omega 0 square. Now what is the Laplace inverse of this? Well, look up your table of Laplace transforms and Laplace inverse transforms, or if you remember it, and this is something you should remember, the Laplace transform of cosine of omega t is given by s divided by s squared plus omega s square. Therefore, s divided by s squared plus omega 0 square will be the Laplace transform of cosine omega 0 t, and this is multiplied by a2. Therefore, the Laplace inverse that we are looking for will be a2 cosine of omega 0 t. Now, this is the Laplace inverse of this thing. So, going back, what will be the function whose Laplace transform is this? I go from this expression a2s divided by s squared plus omega 0 squared to this expression by replacing s by s plus delta omega n, and therefore, the function which I am looking for will be this function, which is what the Laplace inverse would have been if it was the Laplace inverse of this part, multiplied by an appropriate exponential. And what is that exponential? That exponential is e to the minus delta omega n t, and therefore the function is a2 e to the minus delta omega n t cosine of omega 0 t. Or if I write it with omega n in place of omega 0, that is omega 0 expressed in terms of omega n, I'll have it as a2 e raised to minus delta omega n t cosine of omega n square root of 1 minus delta square into t. Now, let us not worry too much about what exactly appear as the argument of the cosine function and the exponential term here, but let us concentrate on their behavior. Of course, it does not require me to tell you that this function is simply an oscillating sinusoidal function which will continue oscillating forever. This part, since delta is positive, omega n is positive, is an exponentially decaying function. And now that we have a product to the two, the exponentially decaying function goes to 0 as t tends to infinity. The cosine function keeps on oscillating between plus 1 and minus 1, and therefore this whole thing will be oscillating all right, but the amplitude of the oscillation will go on decreasing as time passes, and therefore it will be what is called a damped sinusoidal function, which I had mentioned earlier. So, in other words, there will be oscillations all right, but the oscillations will go on decreasing in their amplitude as t increases, and at what rate? That rate is given by the exponent associated with the exponential part. The exponent in this case is delta omega n, and that is given by 1 by tau, where tau is the time constant, or alternately the time constant tau is given by 1 by delta omega n. And as before, if you wait for 5 time constants or for 10 time constants perhaps, the exponentially decaying part is virtually 0, and therefore the oscillations will be almost 0 by the end of 5 time constants or maybe 10 time constants. So, this takes care of one of the two terms. The other term can be handled also equally easily. The other term is given by a3 omega 0 square divided by s plus delta omega n square plus omega 0 square, and I am asking what is the Laplace inverse of this. Now, here I have s plus delta omega n in the denominator, but there is no s or anything involving s in the numerator. So, if I know the Laplace inverse of not this but of a3 omega 0 square divided by s squared plus omega 0 square, then from that I can obtain the Laplace inverse of the function of s that I have already. Now, what is the Laplace inverse of this? Once again, this is something which all of us ought to remember. The Laplace transform of sine omega t is omega square divided by s squared plus omega square. Remember, omega square, not omega, omega square divided by s squared plus omega square. So, this thing is the Laplace inverse or the Laplace transform of sine omega 0 t, and therefore the Laplace inverse of this whole expression is a3 sine omega 0 t. But I do not have s, I have s plus delta omega n, and therefore the Laplace inverse that I am looking for will be given by a3, once again the exponential minus delta omega n t multiplying sine of omega 0 t. So, this is also an oscillating but exponentially decaying function. Now, of course, I have this and I have the other term which is a2 e raised to minus delta omega n t into cosine of omega 0 t, because a2 may not be 0, a3 may not be 0. So, I have two terms. Now, these two terms can be combined to write as simply equal to say some number a4 into the exponential factor is pulled out common, multiplied by cosine of omega 0 t plus what I can write as some angle theta 0. And so it can be seen as an oscillating function which is modulated by an exponentially decaying function, or it's a exponentially decaying sinusoidally oscillating function. Now this is something one comes across, as I told you, in network theory when you look at the response of an RLC series circuit which is connected to a battery through a switch. The capacitor is initially uncharged, let's say, and then you find out the buildup of voltage on the capacitor. Then depending on the values of R, L and C, if the resistance value is not too large, then the circuit does involve oscillations. The capacitor voltage does not build up steadily. Instead, the capacitor voltage keeps on rising but has overshoots and undershoots. Before, after enough time has elapsed, it becomes constant, equal to the battery voltage. So you have perhaps experienced or encountered this function and its graph earlier. Once again, I am not going into an exact sketch, but this is what it will roughly look like. Here is the final value towards which the function is tending, because I have that additional term a1 divided by s, whose Laplace transform is the constant a1. So here is that a1, and here is this additional part which is oscillating but decaying in amplitude, and the whole thing therefore will look somewhat like this. I am drawing this figure only to give you some idea of what it looks like. So I have not been very careful in locating the various points on the graph. So here is the final value, or the steady state value. Starts off with 0 but crosses the steady state value, goes beyond it, therefore there is an overshoot. This is the maximum overshoot. Then start decreasing, crosses the final value once again but does not stop there, goes on decreasing further. So this is the undershoot. Once again it starts building up but goes beyond the mark. There is a second overshoot which is not as large as the first overshoot, then keeps on decreasing but overshoots the mark once again in the opposite direction, or undershoots. The second undershoot is less than the first undershoot, and keeps on doing this, but after 5 or 10 time constant the function is virtually a1. So after 5 or 10 time constants have elapsed, the change in speed will be constant, or the speed will now be at a new value. Now this was what? This was the effect of change in load torque on the change in speed. We are looking at the factor or the amount by which the change in load torque affects the speed, and we see now that in the steady state, when the steady state is reached, the speed will be different from what it was originally, but during the transient state, when we have a pair of complex poles like this, there will be oscillations. So in other words, the motor speed when the load torque is increased will not simply go down to the new value, but it will go down more than it will finally remain at, then keep going up and down like this, and go on oscillating like this till enough time has elapsed. Now this will depend on the nature of the poles of the transfer function, or the nature of the poles or the roots of the factor s squared plus as plus b, and we are looking at various possibilities. One possibility was real distinct roots, second possibility was real coincident roots, third possibility was a pair of conjugate complex roots, and the fourth possibility, which does not arise in this case, is that we have a pair of imaginary roots. We are looking at possibilities for a particular set of parameter values for the motor drive. One and only one of these possibilities will hold, but it's good to know what can happen, what are the various situations which are possible, and this is what we have done. I would leave it as homework to you to look up the section in your network theory course or network theory textbook where this RLC series circuit with a battery and a switch is studied in detail and the response is plotted in full, or look at the corresponding chapter in the control theory book where you look at the response of a second order system to a step input. We will proceed now with feedback. Why is it that we want to introduce feedback, and what kind of feedback, and what will it do? Now what we have talked so far, of course we have gone beyond the steady state, by using the Laplace transformation, by using the idea of a transfer function, and by using the Laplace transformation and inverse Laplace transformation, partial fraction expansion and all that, we are able to find out how the speed varies during the transient period. We are not just looking at the steady state values now. So we have gone beyond saying that, okay, if the load torque was at the nominal value and the motor speed was at the rated value, say 1500 rpm, when the load torque increases to this amount, the motor speed will decrease after some time lag to this amount. So the old speed was 1500, what will be the new speed in the new steady state? That was the very preliminary calculation that we did. But now we are able to go beyond it. We are able to say that during the transient period, the motor speed may oscillate or it may not oscillate. And how long will it take for the final value of the speed to be taken? As usual, it is given by, or it is expressed in terms of a certain time constant. And one will say that 5 to 10 time constants is enough. When that much time has elapsed, you can say that the steady state has been reached. So the Laplace transform technique has enabled us to do that. The Laplace transform technique will enable us to go further now, and that is, we want to look at the effect of feedback. In order to do that, I am going to write down the expression for omega s now in a somewhat different way. Remember what we had done earlier, using the signal flow graph idea, or by looking at the equations and transforming them, we were able to write down omega s as some coefficient multiplying Ea of s and some other coefficient multiplying TL of s, where Ea of s is the Laplace transform of the applied voltage, TL of s is the Laplace transform of the load torque. We are able to obtain these two coefficients, and of course the second coefficient of TL had a minus sign, and so the increase in TL caused a decrease in speed and so on. Now this we can represent for the purpose of further work by a simple block diagram which does not correspond to any actual part or component of the system. And I can represent it like this. I will show here a summation block plus sign, and I will show two incoming arrows. So this is partly the signal flow graph idea, but I am drawing a block diagram. I will have Ea of s as an input to this block, and this block I am going to represent or denote by G A of s. Why A? Because it is something that multiplies Ea of s, and why G? Because it is a transfer function. I told you that in control literature, G is the preferred symbol for the transfer function. Except for feedback path, we use the letter H. Likewise, I have the other term, so I will write this. So I have to change this plus symbol now. Instead of that, if I use the usual black block diagram symbol, I will have the cross type thing with a plus sign here, and anticipating that there is a minus sign here, I will put a minus sign here, and I will put a small block here which I will call G of T for torque S, and the input to that will be TL of S, the load torque Laplace transform. And the output of this device, which has a plus and a minus, although I can have a plus and a plus, then there will be a minus sign associated with GT, will be omega s. So this simply represents diagrammatically in the form of a block diagram this equation. The Laplace transform of the speed is given by Ea of s, the Laplace transform of the applied voltage multiplied by one transfer function Ga of s, minus the Laplace transform of the load torque TL of s multiplied by another transfer function which I am calling GT of s. And this Ga and GT one can calculate, they will involve the system parameters. Now we can see from this that if I increase TL of s, or if I increase or decrease Ea of s, it is going to change omega s in one way or the other. And that is how we figured out that a change in the load torque, an increase in the load torque, will result in the decrease in the steady state value of the speed. Similarly, an increase in the applied voltage will result in an increase in the steady state value of the speed. Now when we did that, of course we made use of what is called the final value theorem of the Laplace transformation. So let us apply that final value theorem once again. If I am looking at the final value of the speed, which is the limit as t tends to infinity of omega t, then what did the final value theorem tell us? That this limit, that is the limit of a function as t tends to infinity, which is called the final value of the function, is given by limit as s tends to 0 of s times omega s. The Laplace transform multiplied by s, the limit of that as s tends to 0. Don't forget this multiplying factor s. It is not the limit as s tends to 0 of omega s. It is the limit as s tends to 0 of s omega s. Very often students forget this factor s. Don't forget that. Of course, one can verify it very easily. If I take omega t equal to constant 1, then the limiting value is 1. Omega s, the Laplace transform is 1 by s. If I forget the s factor, then I have the limit as s tends to 0 of 1 by s. That is not 1, that is infinity. But if I have the multiplying factor s, then of course cancelling s and s, I will get 1. So this is just a way of sort of rechecking that what you have written down is correct or not. But you should remember the correct result. The final value theorem says limit t tends to infinity of omega t is equal to limit s tends to 0 of s omega s. Now here I have omega s consisting of two different terms. So I will have es ga of s tl minus gt of s as the two parts making up omega s. Now if I look at the final value of the speed, then you can see that it will involve the final value of the applied voltage and the final value of the load torque multiplied by Ga of 0 and Gt of 0. Let us go through this a little carefully, although it is really very simple. Omega s equal to Ga of s Ea of s minus, remember now I am writing this minus sign here. Earlier I had a plus here, but there was a minus sign with the multiplying factor, minus Gt of s Tl of s, multiply both sides by s. So s omega s equal to s Gas into Ea of s minus s Gts into Tl of s. And now I am going to use the final value theorem. So I am going to take the limit of this as s tends to 0. With that in mind, then I will rewrite this as Ga of s into s into Ea of s minus Gt of s into s into Tl of s. And now let me take the limit as s tends to 0. So limit as s tends to 0 of s omega s, which is nothing but omega, limit as t tends to infinity of omega t, the final value of the speed, that is given by the limit of this as s tends to 0. Now if Ga of 0 is not infinity, that is I can put s equal to 0 in Ga of s without getting into any difficulty, that is there is no infinity occurring, then I can write this as Ga0 multiplying the limit as s tends to 0 of SES. But what is that? That is the final value of the applied voltage, or in other words it is limit as t tends to infinity of Ea of t minus Gt0 limit as t tends to infinity of Tl of t. So it will be given by the final value of the speed will be given by Ga0 into the final value of the voltage, applied voltage. Let me rewrite it as Ea infinity. This is just a symbol indicating that I am taking a limit as t tends to infinity of Ea of t minus Gt0 into Tl infinity. So these coefficients Ga0 and Gt0 tell you how the final value of the speed is related to the final value of the applied voltage and the final value of the load torque. And from this then we can calculate the effect of change in load torque or change in voltage. If there is a change in load torque, find out what is the new value of the load torque. That multiplied by Gt0 will give you this part. If the applied voltage has changed, find out what is the final value of the applied voltage. That multiplied by Ga0 gives you this part. And so the difference between the two will give you the new final value. Or if we are making no change here, let us say the applied voltage is just remaining constant throughout, then there is no change in the final value of the input from the earlier situation and the new situation, whereas the load torque has changed from one value to another. That change in load torque is what we will substitute here, and that will give us the change in the speed of the motor. So GA0 and GT0 are in some sense two numbers which determine the effect of change of applied voltage and change of load torque on the motor speed, or change in speed equal to GA0 into change in voltage minus GT0 into change in load torque. Now, because GT0 is not 0, when there is a change in the load torque, there will be a change in the speed of the motor. This is the unfortunate part of the drive as we have it without feedback. When the load torque changes, there will be a change in the motor speed. This is not error because of anything other than disturbance. This is an error caused by the presence of the disturbance. The drive can be made to run at the correct speed by choosing correctly the value of the applied voltage when the torque is at its nominal value. This thing is something we have done earlier. Okay, now how can we reduce the effect of the change in load torque on the speed? Can we make it completely independent of the speed? Now, as a first step towards that, we thought of introducing feedback. And what was the kind of feedback that we talked about? We called it proportional feedback. So let us now see what will be the effect of proportional feedback, whether it will reduce the change in speed or the error in operation of the system when there is a disturbance or when there is a change in the load torque, whether we can reduce it. Let us see if we can do that. Now, I will continue with the block diagram that I have drawn just now. So, here is TL of S that goes into the block which I have called GT. Here is another block GA, and into it goes EA of S, and out comes omega S. And now I am ready to use proportional feedback. So, I take off from here. Here is something that represents my tacho generator, K tacho generator. The output of that is the tacho generator voltage. The applied voltage is not obtained now directly, but I obtain it by having what I have called a reference voltage. Then there is this difference device which takes the difference between the reference voltage and the feedback voltage. The feedback voltage in this case is simply the tacho generator coefficient, EMF coefficient multiplied by the speed. This difference is then sent through what is effectively an amplifier, and we have called the gain of that amplifier Ka. In the Leonard type of speed control, this Ka is represented by something which is not that simple. It is a prime mover which drives a generator which produces the output Ea, and the field current of the generator is what is driven by this difference between the reference voltage and the tacho generator voltage. So, this is the new block diagram now for the system with feedback. And now we want to find out how does it affect the relationship between omega S and TL of S, that is the disturbance. How is the speed affected by the disturbance? Will the effect of disturbance be reduced? Of course, how is the speed related to the reference voltage? That is also something which we have to know. Now, we have all the tools that are required or that can be used to solve this problem very quickly. And this is why I had to spend some time on the signal flow graph, the Mason gain rule or gain formula, Laplace transform, transfer function, block diagram. All this is really to enable us to see what will happen. Of course, this is only a simple example. We are going to take a somewhat different kind of feedback, and we are going to study the effect of that feedback, and then we will go to a very general situation. But first, this very specific case. I want to write the expression for omega S in terms of TL of S and ER of S. I want to use my signal flow graph idea, and in this case you will see that it is extremely simple. Here is a signal flow graph which has input ER, TL, omega S is a non-input quantity, The intermediate variable EA of S we are not interested in. I have not even bothered to show the error variable, although here I could put E of S as the error variable. I want to find out this relationship. First of all, we clearly see a loop here. Say I start here, go through KA, go through GA, go through this difference device, come out here, go through KTG, go through this different device, and you come back. So there is a loop. Yes, there is a loop. And what is therefore the loop gain? There is only one loop. And what is the loop gain? Remember the symbol for the loop gain L. Here is the loop. What is the loop gain? Starting here, I have KA multiplied by GA. Then I go with a plus sign, so that then I come here, K taco generator. But then here I go through a minus sign. So into minus 1. Or the loop gain is minus KA, K taco generator into GA. That is the loop gain L. What is the next quantity which is to be determined using the signal flow graph and Mason formula? Delta. What is delta? Delta equal to, remember, 1 minus sum of all the loop gains. We have only one loop, so 1 minus L plus the sum of products of two loop gains for non-touching loops, but there is only one loop, so there is nothing more. So I have simply delta equal to 1 minus L, or delta equal to 1 plus KA, K taco generator into GA. This is what I have for delta. Now I am ready to write down the expression for omega S equal to, there will be a transmittance from EA of S and there will be a transmittance from PL of S. Remember, all these transmittances have the same denominator. So in the denominator I will have 1 plus KA, K taco generator GA. I am not writing the S here explicitly. Here also I will have the same 1 plus KA, K taco generator GA. Same denominator for both the transmittances. What about numerator? For the numerator, I have to look at the forward path. Now what is the forward path from ER? This should be ER of S, not EA of S. I have to look at the forward path from ER to omega. There is only one forward path. And what is the gain of the forward path? I go through this with a plus sign KA, then GA with a plus sign out to omega. So the gain of the forward path is simply KA times GA. So let me write this down as KA times GA. That's the gain of the forward path from ER to omega S. That multiplied by what remains of delta. But what remains of delta? Only 1, because that forward path touches the only loop that is there. So delta for the numerator is simply 1. The other path from the load torque to omega S, that goes through GT with a minus sign here. So it will be simply minus GT. So I will write here minus GT. That multiplied by what remains of delta, but what remains of delta once again is only 1. So this is all that there is. So this is the expression for the speed in terms of the Laplace transform of the reference voltage and the Laplace transform of the load torque. Let us compare that with the earlier expression that we had, which was simply omega S was given by GA of S, let me write that S explicitly, into EA of S minus GT of S into TL of S. So what has now happened is the following, and let us look at the torque term first, because that is the disturbance variable and we are interested in reducing the effect of the disturbance on the system performance. So let us look at that part first. Earlier it was simply GT, or with a minus sign minus GT. Now it is what? Now it is minus GT divided by 1 plus KA, K taco generator GA, and this KA, K taco generator GA is simply the loop gain. If there was no loop, if I remove the feedback path, go back here, if I remove this feedback path, there is no gain, and if I take this as my EA, then there is only GA. Because of the feedback, there is a loop created, and because of the loop, now in place of 1 in the denominator, I have 1 plus something, and so the denominator is going to be greater than 1. Therefore, I have GT divided by a number greater than 1. Earlier I had just GT. So, the effect of the load torque will be reduced, and will be reduced by what factor? By this factor 1 plus Ka K tachogenerator Ga. Or if you want to look at the steady state values, then I have to put S equal to 0. So, the use of this feedback will be that the steady state error caused by a change in the load torque, that is caused by the disturbance variable, will be reduced by the factor 1 plus Ka K tachogenerator Ga 0. Let me write this down. In place of 1, I have now 1 plus Ka K tachogenerator into Ga of 0. Now, this can be not small, it can be even comparable with 1 or even larger than 1, and if it is so, then the effect of the disturbance will be reduced very much. For example, if I can make this equal to 10, let us say, then earlier I had GT, now I have GT divided by 11. So, effect of the load torque or the disturbance will be reduced by a factor of 11. So, if earlier the change in speed was 11%, now with this the change in speed only will be 1%. So, how can we reduce the effect of the load torque changes? Can we make it absolutely 0? No, we can't. We can make this term large. I can make this instead of 10, 100, then the effect will be reduced by 100. But I can't make this infinite, because this is just gain of that error signal, so called error signal, to the armature voltage input, tachogenerator coefficient, and Ga0, the value of the transfer function involved that multiplies the motor voltage at 0. So, this cannot be made infinite, but it can be made large. Unfortunately, as I have been telling you earlier, we are only looking at steady state. The effect of making this large will be to reduce the steady state error caused by the disturbance. But what about the transient behavior? And we will see very soon that the transient behavior can become bad, in the sense, originally without feedback the speed may be just changing from one value to another without any oscillations, but with feedback the speed may now perform oscillations before going to the new value, and the oscillations need not be small. Although the error may be small, the oscillations could be large, and this is something we are going to look at as our next topic. But before we get into that, let us look at the other term. What has happened now is ER is multiplied by this expression. Earlier EA was multiplied by GA of S. So, now this 1 plus Ka K tachogenerator Ga is occurring in the denominator here also. So, that means the value of the applied voltage which was used earlier will not be now the value of the reference voltage, and this is of course something we have seen already. I was talking about in the numerical example armature voltage of the order of 230 volts, and whereas I was saying that the reference voltage may be of the order of 20 volts. But that is alright, because this EA is multiplied by GA, whereas ER is multiplied by GA into Ka divided by this denominator factor 1 plus Ka K tachogenerator Ga. And therefore, we can find out the appropriate value of the reference voltage, so that under rated conditions the speed will be at the nominal value, and we can complete this by using the final value theorem. Therefore, I will be able to write omega infinity, the value of the motor speed after enough time has elapsed, will be given by Ka into Ga0 divided by 1 plus Ka into K tachogenerator into Ga0 multiplying the reference voltage, the steady value of it, minus the second term will be Gt0 divided by 1 plus Ka K tachogenerator Ga0 multiplying the steady value of the torque. So, if I know what is the required steady value of the speed, if I know under what torque condition I want that value, I know TL infinity, then if I know the tachogenerator back EMF or voltage coefficient KTJ, if I know Ga and Gt involve the parameters of the system, I can calculate and I choose the value of Ka, the gain of the amplifier, so to speak, I can find out the reference voltage that needs to be applied to produce the correct speed. So this drive will then run at the correct speed with an appropriate value of reference voltage when the load torque is at the nominal value. The signal E that I talked about earlier, the output of the comparator, will not be 0, but that 0 is not a steady state error at all. There is no steady state error at rated torque conditions. However, when the reference voltage is kept unchanged, of course, and the load torque changes, then there will be a change in the speed, or there will be a steady state error in the speed. However, this steady state error in the speed when the load torque changes will be much less with feedback than what it would have been without feedback. And the factor by which we have been able to reduce this error caused by load torque changes is given by this 1 plus L0. And very often L0 is much greater than or is greater than 1. Therefore, it is this loop gain, its value at s equal to 0, because there is a transfer function involved. This loop gain is what determines the reduction in the effect of load torque changes. So what appears as a gain is really a gain in the sense of the term. The higher this loop gain is, the lower will or the lesser will be the steady state error due to load torque changes. But to remind you once again, this L0 increase will go with a worse performance in the transient state. That is, as the speed changes from an original value to a new final value. And this is what we will take a look at after we have looked at another feedback scheme which I had mentioned long time ago. What we have looked at right now is only proportional feedback. We will look at another feedback scheme, which is what it was called integral feedback. And we will see that with integral feedback, the effect of the load torque changes can be made 0. That is, no matter how the load torque changes, if it changes from one steady value to another steady value, the motor speed, although it will change during the transient period, will go back to the desired value. So the system will operate without steady state error caused by disturbance input or by load torque changes. We will see how the integral feedback achieves this thing. Once again, there will be a negative factor associated with this, namely transient performance. We will have to look at the transient performance when we have integral feedback, and we will see that with integral feedback there is a danger that the transient performance will become even worse than it is with proportional feedback. And for that we need additional methods of investigation, and one such method I mentioned to you earlier is called the root locus method. So we will first look at the integral feedback and then we will go on to the root locus method.